Hi, this is Rob Furnett with a video presentation of my final project for CSCI E-222, Foundations of Large Language Models at Harvard Extension School in the spring 2026 semester. For this project, I built an agentic coding system that generates Python solutions to benchmark coding problems and then improves them through test-driven self-correction. The focus of the project is on practical LLM tool use, not just one-shot text generation. The main challenge is that code generation should be evaluated by what executes correctly, not by what merely looks plausible. In benchmark settings, a solution either passes the tests or it doesn't, so subjective quality isn't enough. That means an effective coding agent needs a real feedback loop. Write the code, run the tests, inspect the failures, revise and repeat until success or resource limits are reached. The evaluation in the project uses two standard public coding benchmarks, MBPP, or Mostly Basic Python Problems, and HumanEval, both from Hugging Face. For the main study group, I targeted 664 total tasks by combining both datasets. I also support smaller or stratified subsets so experiments can run faster and at lower cost while preserving objective pass-fail scoring. This system uses two pre-trained models in inference mode. Claude handles the coding and decision-making inside the tool loop, and CodeBERT is used separately to create embeddings for analysis and visualization. So there's no fine-tuning pipeline here. The focus is on orchestration, execution feedback, and evaluation. The backend is a single FastAPI service that handles solving, code execution, benchmark listing, and persisting run history. SQLite stores all benchmark problems, agent runs, and per attempt records, and Hugging Face datasets populate the problem database automatically on first startup. Generated candidate code runs against the benchmark's assert statements in a sandboxed subprocess, so execution happens in the back-end process and not inside the model weights. For orchestration, I used LangGraph to implement two nested graphs. The outer graph manages self-correction rounds. If the benchmark tests still fail after an attempt, it starts another up to the configurable cap set in the environment file. The inner subgraph manages the back and forth between Claude and the tools within each attempt. Claude calls run tests or check syntax. The tool runner returns real standard out and standard error messages, and Claude uses that output to revise its next attempt. Both limits are environment variables, so you can tune the trade-off between thoroughness and API cost without changing any application code. The diagram on this slide shows exactly how these pieces connect. A client, the Jupyter Notebook or the Gradio UI, or any HTTP caller, sends a solve request to the FastAPI, which handles HTTP, persistence, and problem seeding. Inside, LangGraph's outer graph coordinates the self-correction rounds, and within each round, the inner subgraph runs the Claude to tools loop. Claude sends the tool use message to the tool runner, which dispatches to run tests or check syntax, and returns the tool result message containing the real output and pass-fail result. As mentioned, the actual code execution happens in a sandbox subprocess. On completion, FastAPI persists the agent run and all attempt records to SQLite. In the pilot run, I evaluated 100 problems, 50 from MBPP and 50 from HumanEval, and the overall pass rate came in at 96%. The chart on the right shows that by dataset. HumanEval reached a perfect 100%, and MBP came in at 92%. The chart on the left breaks down where those 96 successes actually came from. 83 problems were solved on the first attempt with no self-correction needed. 13 more were solved after at least one retry round, and 4 were never solved within the allowed outer rounds. The diagram on the left of this slide shows the distribution of wall-clocked solve times across the pilot. Most runs completed in under 15 seconds, with a median of about 10 seconds, and the tail extends towards 60 seconds for the hardest cases. The box plot on the right separates those numbers by outcome. Passing runs had a median latency near 10 seconds, while failing runs had a median near 38 seconds, because the agent spent time exhausting its retry budget before giving up. These charts track inner subgraph activity. The left chart shows that most problems needed just 2 or 3 tool calls in total. The right chart shows that no run hit the inner turn cap. There are 3 main strengths of this implementation I want to highlight. First, grading is grounded in actual execution, where candidate code is run against each problem's assert lines in a sub-process, so pass-fail matches the MBPP and HumanEval evaluation standard, and the model can't vouch for its own output. Second, there's a clean separation between the backend, storage, and clients. FastAPI, SQLite, and a single HTTP API serve a 100-problem batch study and a one-off demo through identical code paths. And third, the agent depth is explicit and fully observable. The outer and inner loops are configurable in the environment file, and every solve call returns a full trace with tool steps, standard out, errors, and latency per attempt. There are also 3 honest weaknesses worth acknowledging. The sandbox is good enough for a research demo, but code runs in a child process on the same machine as the API. That's not the kind of lockdown environment you'd want for untrusted code. Also, the retry cap can stop the agent before it finds the fix. In the pilot, all 4 failures hit the outer cap, meaning the agent was still actively trying when the budget cap ran out. And results are tied to the specific Claude model in use. Switching versions, hitting rate limits, or running large batches without cost planning will change both speed and pass rate in ways that are easy to underestimate. Looking ahead, there are 3 natural directions to take this work. The most important is stronger isolation for code execution. Moving from a hosted sub-process to containers or a remote judge service, such as running on cloud infrastructure, would make the system safe enough for untrusted input and practical to scale. Second, the agent would benefit from richer tool feedback. Adding linters, type checkers, or diffs against the previous attempt would give the model more to work with during each repair step, without changing the outer-inner graph structure. And third, the evaluation needs to go broader. More benchmark slices, confidence intervals across multiple seeds, and per row logging of model ID, caps, and costs, so results are reproducible and comparable over time. Now, with that understanding of this project and implementation, let's take a look at a demo. The application has 3 components: a FastAPI backend, a Jupyter Notebook for testing, and a Gradio UI. To run this app, you'll obviously need Python installed, as well as the UV package manager and an Anthropic API key for the Claude LLM. To get started, after you clone the repo, launch a terminal in the root folder and copy the .env.example file, save as a .env file, and enter your Anthropic API key. Be sure to do this in the .env file and not the .env.example file, as the .env file is get ignored, so it won't expose your API key if you push this project to your GitHub repo. You can use the default values for the other variables in this file, or feel free to modify them if you want to use a different Anthropic model or have the agents run through more iterations of the code generation and self-correction LangGraph workflow. After saving your updated .env file with your Anthropic API key, launch the startup shell script, passing the --all flag to launch the backend, notebook, and Gradio UI. Note that if you get a permission denied error when launching the app and you're in the root project directory, run the following command to ensure the file is executable. Now, it will take several seconds to initialize the application, but once you see the running on local URL message, the app has been initialized. And to test the FastAPI server, you can launch a browser and go to 127.0.0.1/8000/docs. Then test the /problems/list route to see the list of coding benchmark problems. And the /problems/summary route to see counts of the benchmark problems. Both of these routes are pulling data from the MBPP and HumanEval datasets, which were pulled down from Hugging Face when the app was initialized. You can also hit the limits route to see the values set up in your .env file, as well as the models route, which will go out to Anthropic using your API key from the .env file and pull back a list of available models you can use for your agent. Now that we know the backend is up and running, let's launch the notebook on 127.0.0.1 port 8888/lab. Then open the evaluation.ipymb file. Okay, with the notebook open, note the max problems variable in the first code cell. This is where you control the number of problems to solve, and you can see it defaults to 10. Set this value to whichever number of problems you'd like to run against in the notebook. After the notebook finishes running, you can scroll through and see a detailed explanation of the performance. Now, with that walkthrough done, we can launch the Gradio UI on 127.0.0.1 port 7860 and test that out. The UI has two tabs: Solve, which allows you to select a Claude model and a problem to solve, then run the code generation and evaluation workflow, and a Results tab, which allows you to select a specific problem run and see how the model did. Here we see that there were 10 total problems run, which we did in the notebook, and all 10 passed with 100% accuracy. Next, we'll select a specific problem, then fetch results, which we see here. Now, back in the Solve tab, we'll select a problem from the dataset, then change the Claude model from the default Sonnet 4 to Haiku 4.5, then run the agent. And here we see Haiku was able to solve the problem in one iteration of the workflow. Now let's try another problem. And it did well again. So let's see if we could find one that this model may have trouble with. And here we see it failed to solve the problem after both iterations. Now let's change the model to Opus 4.6 and run again. And we see Opus was able to successfully solve the problem in its first attempt of the workflow. So that concludes the presentation of my final project. I hope you found it interesting.